Hello, my name is Friedemann Zenke. I'm the head of the computational neuroscience team at the FMI in Basel, and I'm very happy to show you today SpyTorch, how to do surrogate gradient learning in spiking neural networks in just 20 minutes with PyTorch. So what we want to do is essentially build a task-optimized spiking neural network the same way you would build an artificial neural network in machine learning. And to do this, what this requires is first to specify the input data that you're going to deal with. That's shown here on the left-hand side, and a desired output for the network, which is shown here on the right-hand side. And that in a way defines the skeleton or scaffolding for the computational function you want the network model to implement in the end. And once you have that, you can worry about how do you set the connections in your spiking neural network model, how you find the right connectivity. And the way we're going to do this is by using surrogate gradients. So let's look briefly at the input side. Typically in the spiking neural network, you might be dealing with input spike trains, which encode information in a spatial temporal way. So here's an example for a little spike train in response to a simulated idealized binary discrimination task, which for instance, an animal might face in the real world. You have multiple input neurons here on the x-axis and the y-axis, and you have time on the x-axis. And then this is a spike raster plot defining when a certain input neuron spikes. Similarly, a different texture, for instance, might evoke a different spatial temporal input pattern in your barrel cortex if you happen to be a rodent, as in this case. So this would be a typical input encoding for, in this case, a biological neural network. And of course, you would assume that somehow the data, the spike time, has some underlying structure, which can actually be decoded by the spiking neural network. That way, you can define a classification problem. Now, how about the output abstraction or the output encoding that you have to fix? So we move to the output end of the network here, which of course contains spiking neurons by definition. And to facilitate our learning process, what we're always going to assume is that there is a small population of readout neurons. So in our example here, we were dealing with a binary classification task. So let's assume there are two readout neurons, which are essentially computing a linear combination of the filtered output spike trains in this output layer of the network. And these activations may look like this over time for these two neurons. So what this allows us to do is now to look for the maximum of these curves. And that's one of the assumptions we're going to make in the following, to reduce the output activation in time, basically. Right, so reduce the temporal component of it. So we're going to look for the maximum of these two curves, and that allows us to put this maximum into a softmax activation function the same way you know this from artificial neural networks, which again then allows us to compute a binary cross-entropy loss. Sorry, a cross-entropy loss. The next thing you need to know is how do you train this network? And for this, we have a little interlude now, which is going to show you that spiking neural networks are recurrent neural networks in a computer science sense. What I mean by that is that spiking neural networks are stateful, even if they don't have explicit recurrent connections, simply because neurons have an internal state. And to illustrate this, I'm showing you here the output of a very simple neuron model, the so-called leaky integrated fire model, which has a membrane voltage, which evolves over time as shown here. And in this case, it has a current-based synaptic input shown here in this variable I in gray. And whenever this neuron receives one input spike at a dedicated time, this current variable makes a jump, which is defined, or the magnitude of the jump is defined by the afferent synaptic weight that this presynaptic neuron is connected with to this postsynaptic neuron. And this jump triggers an excitatory synaptic current in this case, which then is translated into a membrane change. And if there's enough input, as shown here in the end, this postsynaptic neuron actually starts firing. So the way you would implement this is, in the simplest case, through the forward Euler integration method, which is here in a very simplified form is shown here. The equations where the input current of time step n+1 is given as a function of the input current at type step n plus feed-forward synaptic input. If you're dealing with a recurrently connected spiking neural networks, you'll have an additional term which corresponds to recurrent synaptic input. Now this variable I feeds into this variable U, which again is recursively computed in time and here. We can also graphically represent this as a computational graph, where you have the input spike trains here coming in at the bottom. They're feeding into this current variable, which again feeds into the voltage variable. And only when this voltage variable hits a certain threshold, as depicted here in this last equation at the top, it's determined here by the Heaviside function, which implements a threshold. Then there's an output spike that's generated in this discrete time step. And this output spike is fed back both to other neurons through synaptic connections, but also to the voltage itself as a reset current, which makes sure that the neuronal reset is implemented. So why is this important? This is important because this means that spiking neurons, even one single one, is technically a recurrent neural network due to this temporal aspect, in which time steps depend on previous time steps. And importantly, we know that there are training procedures for this to compute gradients, also in networks with hidden units. And namely, there is backpropagation through time, BPTT, and real-time recurrent learning, RTRL. So there's one big problem with this, and this problem lies in the Heaviside function. So if you're trying to compute now gradients of the system, you will run inevitably into this problem that there's a hard threshold nonlinearity, namely the Heaviside function. And when you compute a derivative of this, it's either 0 or it's infinite when you happen to be right at the threshold theta in this case. And in consequence, there's no gradient. So there's no gradient that you can walk down in parameter space. If this is parameter space, then it means your loss function is flat essentially everywhere, except in these places where there's a cliff. So you can't use this for gradient-based optimization because the derivative of the spikes is ill-defined. And the solution we're going to use are called surrogate gradients, where the idea is whenever we compute derivatives, we use a surrogate derivative, which corresponds to a nonlinearity, which is not the Heaviside function, even though in the forward pass, we're using the Heaviside function for computing the activity in the network. And when we do this, we end up with a surrogate gradient, which under relatively broad conditions is something we can use for optimization. And to illustrate that this works, we've prepared a bunch of notebooks, Jupyter notebooks, which you can openly access here on GitHub. One disclaimer, or two disclaimers actually. First of all, these notebooks are self-contained for didactic reasons, so there's much better ways of writing code using units and functions. Here it's all in one notebook. So I encourage you, if you actually end up using this, to write your own code, which goes beyond one single notebook. And the second point is that PyTorch auto differentiation is a major convenience for us here to actually compute the surrogate gradients, but the lack of efficient sparsity supports in PyTorch and also TensorFlow nowadays makes simulating spiking networks quite inefficient. That's something that's basically work in progress that people work on making this more efficient, but currently is something we live with for the convenience. So when you go on this link, you'll find a bunch of notebooks, and I'll just walk you through the first one. And I'll let you explore the other ones later. So this one really gives you the essence of what's important. So I've basically just walked you through the fact that spiking neurons are RNNs, which you can draw as a computational graph on which you can perform backprop through time. So that's the basis for why we're going to use PyTorch in this case, which is a library with auto differentiation support. And we're going to build a very simple network here, which has an input layer consisting of 100 input neurons. And then it has a hidden layer with 4 hidden units. And then it has 2 output units because we're going to do the simple binary classification problem that I've mentioned earlier. Here we define some global variables, a time step, which we choose to be 1 millisecond. And in units of seconds, that's 10 to the minus 3. And we're going to say we want to simulate this network for 200 time steps, so 200 milliseconds. We also define a batch size, which will become more important during training. So now we just generate an artificial data set for the sake of demonstration. And we're going to create just some random Poisson spike trains of these input neurons, these 100 input neurons, with a frequency of 5 Hertz. Effectively, we generate one batch of size. What was the size again? 256. What you get out is a data batch X data, which has spikes that look like this, right? So it's like a spike raster with firing times, which look random because they are random at a certain firing probability. Now we assign random labels to our entire batch to come up with a binary classification problem. And that's the setup really of the data. Now to our network model. First of all, we'll implement the leaky integer finder that I've shown you. So we'll use a membrane time constant of 10 milliseconds and a synaptic current time constant, decay time constant of 5 milliseconds in this case. And we'll define these helper variables alpha and beta as so. And they will allow us to write down the leaky integer finder dynamics more compactly. Now we define the input weights, W1, and we initialize them from a normal distribution of given mean and standard deviation. And we also define the readout weights. Remember, this is a 3-layer neural network if you want. Right, and now we can define our spiking neurons. And we'll also implement our spiking nonlinearity, first the naive way to show you how it fails, where we simply say, okay, we output a 1 whenever the input to the spiking neuron exceeds this threshold of 1. We just define the threshold, in this case, the threshold is 0, or later we subtract a negative bias term of 1. So putting this all together in a simple simulation loop that effectively implements the two equations that I've shown you earlier, where we have the new current variable I called on the previous slides, which involves multiplying this with the previous state of the current variable plus the input. And here that's the voltage equation, where we have this term which takes care of the reset in this case. So whenever there's an output spike, this variable RST, short for reset, will be 1, and the whole thing will be set to 0, which is our resting potential, and otherwise it will just integrate things up. Here is the decay of the membrane potential, and these are the current inputs. Additionally, we add some support here for recording things so we can plot them later. Okay, let's run this. If we run these dynamics for some inputs, you see that these voltage traces that come out, they look like simple leaky integrated fire voltage traces. And if we now want to do training, and here we go into the section with the supervised learning, so training it. What we define here is the parameters that we want to optimize. So these are the weights of the network. Here we define the optimizer we're going to use. We're going to use Adam, which is a standard optimizer in machine learning. And then we have the softmax function here and our non-negative log likelihood loss. Together, this gives our cross entropy loss. Good. So putting it all together, we run this over 10 epochs, 1,000 epochs. And here we do the optimizer step after computing the loss value of the network. And what you can see is that the loss does go down, but not very much. And that has to do with the fact that essentially only the readout weights are learned. So if there happen to be, due to an initialization, some spike that happened in the hidden layer, then we can improve something with that, but otherwise gradients won't propagate. And this is also reflected here. If we look at the accuracy in the end, it's around chance level. Remember, we assumed the patterns are random, they distributed plus minus 1, or 0 and 1. And chance accuracy should be 50%, and that's essentially what we're getting. Good. Now comes the trick. So now comes the surrogate derivative. So to implement a surrogate derivative, we have to hack a little bit with PyTorch, but it's very simple. The only thing you really need is to define your own class, which we call now surrogate gradient spike in this case. And it inherits from this autograd function in PyTorch. And you have to define these two static methods, and that's all. This one defines the forward pass, and you will recognize the heaviside function that I had already implemented earlier that implements the spike if you're above this threshold 0. And here we're saving a context, which we need for the backward pass, basically stores the input. And then we have the backward method, which is what you need to compute, pretending that in the forward pass you'd used a fast sigmoid, as we've used, for instance, in our super spike paper with Surrogate and Woolley. And that's all. That's really all. So then PyTorch still requires you to define this new spike function as applying this class that I've just defined. Here again, we initialize the hidden layer and it weights de novo. And we set up the same kind of learning loop that we set up earlier. And now if you run this, we plot the loss of the surrogate gradient versus the loss of the true gradient, you can appreciate that this really learns much better because now also the hidden layer really learns. Here again, some output voltage traces for comparison. And in the end, you can see that the accuracy in this problem is much better. So of course, there's no real structure like in this data set because it was random data. So we're trying to overfit random data. So that's why in tutorial 2, we'll show you how to use a slightly more difficult data set. Specifically, we're going to use the fashion MNIST data set. In this case, it's an imaging data set, and we'll use a current to firing time encoding to convert pixel intensities to firing times. And what you'll learn is how this network classifies. And in the end, you will appreciate here some hidden layer spikes of this model after it's been trained on fashion MNIST. And it does so with a training accuracy of approximately 90%, which is not too bad. It's not great, but it's also a very small network. And test accuracy is around 86 in this case, but it definitely has learned something in its hidden layer. So you'll see there are more notebooks in here. I'll just skip right to the fourth one, which now uses an even more sophisticated input. In this case, these are spoken digits that have been processed through an artificial cochlear model, or basically a model of the cochlear nucleus, if you want to be precise. This is the details I described here in this publication by Benjamin Kramer. These are now your input configurations to the network. And again, here we're showing you how you can train this network with one hidden layer and recurrent connections in this hidden layer. Here are again some example spikes in the hidden layer, showing you that this is truly a spiking neural network. And again, here you have the accuracy, which for this data set is not terrible. So it's definitely better than chance, which would be 10%. No, actually would be 5% because there are 20 classes in the data set. So here we're at around 70. And it gives you ample of opportunity to play with. Right, that's all from my side at the moment. So I hope you can enjoy these tutorials. Again, you can find them here if you go to github.com/fzenki/SpyTorch, or you simply Google for SpyTorch, spiking neural networks, and you'll get there. And I hope you find them helpful. If you find any bugs or have suggestions for improvements, feel free to open a ticket and report an issue. That's all from my side. Thank you very much for your attention, and have fun coding with spiking networks. Bye-bye.